welcome guys. I think we should start. My name is Stanley. I worked in Photoneo for a couple of years as a programmer, as a support technician, and a lot more. Today I'm going to tell you a little bit more about the beam picking studio and a little bit of theory. We are going to pig into the studio itself, so I'm going to introduce you to all the steps required for you to be able to get the CAD files, the robot, scanner, and everything, put it into the studio, and end up with a functional solution, functional project. Today we are going to go through a couple of slides, a little bit of the theory for the machine vision itself, for the accuracies of the robot, for why beam picking in general. Then in the middle of the training, I'm going to skip and go to the beam picking studio, and I'm going to go through the process, and so you can see it, how you can do it. And then at the end of the day, we should have a functional beam picking system, beam picking setup with a robot picking the parts. Just to pick the parts will be like this. We have a full bin of the parts, a scanner, the robot, everything. Okay, so if you're ready, I'm ready. Let's begin with the beam picking studio. Take a picture. Take a picture, right? Take a look on this picture and see. This is something you may be really familiar with, and these robots are actually in the industry for a lot of years, for decades. The robots are built to replace a human where the human is not accurate enough. I mean, in the terms of repeatability and accuracy itself. They do a lot of tasks. Usually it is some kind of welding, gluing, or just assembly. And they carry heavy things, they carry small things, they carry everything. There are a lot of the robots in the industry. But if you think about it for a couple of minutes, these robots are made to do repetitive tasks. They do something from the morning to the evening, maybe through the night, and they do the same task all over again. So they have a programmed path. They're versatile, so you can use them for many projects, for many reasons, and you can program them path, you can program them some actions, but after you program them, they will do only the same task from the beginning to the end of their lifetime. With vision guided robotics, we have a little bit of experience. A lot of the vision guided robotics is built on the top of the two-dimensional cameras. You may be used to smart cameras with processing in them, or just dumb cameras connected to the vision systems, and then the vision systems processing everything. And in vision guided robotics, we have multiple use case scenarios, but there was a limitation for the third dimension. So usually these tasks were static in terms of position, right? You can have something on a conveyor belt and the camera looking at it and doing some inspection, for example, and then sorting out the bad things. Or with the robotics, you can have a piece in the robot, then the camera take a look at it and maybe rotate it for desired angle or something else. But this is not really covering all of the things the human usually do as operators, right? So couple of examples what we do with the vision for the robots to be able to do tasks like a human is usually a pick to order e-commerce, so depalletization, trajectory correction, machine loading, packaging, sorting, a lot of the stuff which literally require third dimension, which are not enough to do with two-dimensional camera. Another topic is the accuracy and repeatability of robots. We are going to focus on this topic today as well. And on the picture on the right, you can see a couple of examples for good and bad repeatability, and also good and bad accuracy, and the combinations of these two. So top left corner is bad repeatability, bad accuracy. This is something a human would do. They would just do it with some kind of accuracy. If we increase the repeatability, but we are going to be inaccurate. This is the common problem with the machines, because we tend to build them some way based on some CAD files or in general some blueprints, and then we assume that we build them correctly and perfectly, but the reality doesn't correspond to a math model. So we had a bad repeatability, a bad accuracy, and good repeatability, because this motor is going to the very same position every single time. But the arm length of the robot is usually just a little bit crooked, but at the end of the day, this little deviation, like 100 microns at the beginning of the chain, of the kinematic chain, will result in bad accuracy at the end of the effector, right? When you have a long arm, a little movement over here is going to make a huge difference at the end. I'm going to take a look into the chat, because I feel that I'm talking a little bit too fast. So if I'm talking too fast, just let me know. I can slow down a little bit. If I'm talking too quiet, just let me know. Yeah, anytime. I will be glad if you guys have the most of this webinar. And if we combine the good repeatability of the robots with some kind of calibration, we usually have a good repeatability and good accuracy. And this is particularly important for the beam picking in general, because we cannot program the path when we can focus on repeatability. We need to have accuracy as well, because we are going to compute the path from scratch every single cycle. And that's where the accuracy kicks in, and we can have a good results and bad results based on how accurate is our system and how we thought about the design gripper in the beginning. And talking about the beam picking, the last thing, why we do it, why we focused on the beam picking, it is considered as a holy grail insight for the robots. This is task you see a lot in the industry, and these operators have a really boring job to just load something to the machine. It's not a human work usually, and I believe, me personally, I believe that this is something humans should not do. Yeah, humans should do some other tasks, some creative tasks maybe, not just taking stuff from the bin and putting it into machine or else or otherwise. So it is from the top, on the first look, it is a really simple task, but when you think about it, it's a really complex thing. And experienced robotics and programmers have a hard time to do a beam picking from scratch, because it involves a lot of cases. With beam pickings, we can have multiple, and from the left to the right, there are simple and the hard ones. In the left, you see something in organized or in structured, what is it, some kind of plastic shelf or something. So the robot has easy task, localize the whole thing, and then just adjust its work object. In the middle, there is semi-structured beam picking, because we have some kind of pattern. We have a stack, but the stack is moving a little bit from the left to the right. But this is a little bit. It's not really a complicated task, because we have almost always the same orientation in XY rotation. Just the Z rotation is usually moving when we're looking from the top into the bin. And on the right picture, we have totally random beam picking, which is literally the holy grail inside to solve this, because the first thing would be to see what is in there, and then we are not finished. We need to remove this object from the bin, retrieve it. And these are two very hard and very complex tasks, and we will be talking about them today. And why is it difficult? And I already mentioned that you have some kind of skill set in robotic guys, in programmers, but the beam picking requires a huge pile of all other skills or a bunch of people to solve it. And if you think about it, you literally need to know basics of, not the basics, not the fundamentals, but deep knowledge about the mathematics, the physics, the kinematics. Usually it involves some kind of Linux operating system, a little bit of 3D vision theory, algorithms and stuff. Also, all these things are necessary for you to be able to do a beam picking. But if you are doing it from the scratch. In Photoneo, what we do is we extend the robot capabilities with our system, and you may be used to have this scenario with a lot of two-dimensional cameras. When you put some kind of camera, this is robotic arm, you know, and you put some kind of camera in here, and the camera is looking into the scene, analyzing things, taking pictures, processing them, and then telling the robot how to adjust its trajectory, for example, in XY coordination, or how to rotate the last link, right? And with Photoneo, this is not just one device, we have two devices, but they are interconnected, and we basically extend the capabilities of the robot as well via the vision controller and the scanner, which is taking pictures. This is the short video. I'm going to just quickly play it without the sound because you can take a look at it on our YouTube page. I will totally recommend you doing so, because we have lots of interesting videos and we are going to put more and more stuff into the YouTube channel, so don't forget to subscribe. And on this specific video, you can see a huge extra large scanner looking from the distance of 4 meters on little shiny what are these cylinders? They're used in the cars, in the suspension system. And these are with chrome finish, and the robot is able to pick them in 5 to 6 seconds of cycle time. Yeah, this was not something I would consider an easy task even for the beam picking studio, but it is possible, and we did it. And it is running since 2018. So more than 2 years in production, right? This is some kind of thing you can expect the beam picking studio will be able to do. All right, and this is another example with little bit of the music and the text behind it, but I'm going to cover what is in there. You can take a look at this video on the YouTube. I would like to remind you. And this is a manufacturer of air conditioning systems, and they have a problem with leakage, you know, with the gas leakage from some heat radiators. And in automatic assembly line, they usually do it by hand in before to go through the process and scan with the probe if there is some kind of leakage of the gases. So they pump the gas into the heat radiator, and then with our system we do a trajectory correction, and we navigate the robot into the correct position every single time based on how the heat radiator will arrive on the conveyor belt. So this is another example of what you can do with beam picking. So I'm going to skip it because you can take a look at the full video on our YouTube page. And we are going to continue. I'm going to take a peek into the chat if we have any suggestions, anything. Okay. I think there was some sound problem. I hope you have it fixed. Otherwise, you will receive a copy of recordings. Anyway, the motivation behind the beam picking studio, I was talking about how hard and how difficult it is to make beam picking from scratch. And the motivation behind the beam picking studio is so you can do it easily without all that deep tech knowledge. And we have a team of guys implementing beam pickings, usually in the Europe, but let's say all over the world, because we have some beam pickings in Asia and USA also. And then these guys come back to our headquarters and discuss with managers and discuss with programmers, and we evolve Beam Picking Studio, we implement stuff they see, they need, and they find crucial for you to be able to easily integrate beam pickings. So this is how we do it. This is our motivation, why we do it in this way, and that's why I think that the product has good shape. I mean, I received a lot of how to say it, lot of, yeah, I'm stuck. Okay, a lot of guys was telling me that the user interface is really good. Yeah, it's easy to work with. So I think this is basically because of this motivation, right? Okay, enough theory. This is how we do it. So the components is Foxy scanner in here, looking straight downwards. Then some kind of software we have in the vision control. You cannot see it right now because it is streaming, or actually this presentation and everything. Then we have a software path planning and communication with the robotic controller and robot. Right, and the robot is executing the trajectories we are providing to him. For the localization engines, we have two kinds. The first one is CAD-based. It's analytical solution to a problem. So we have this point cloud, like on the picture on the right, the point cloud and the CAD model. And if you see, this is the CAD model. This is something you can have in your factory, and it is going in this bin, the very same part every single time. I see a raised hand, so maybe I'm going to check. Okay, so this is a question, so I'm going to answer it later. Anyways, the localization engine, the analytical one, will take the CAD file, will take the point cloud scan from the surface of the bin, and then it will try to find with some analytical methods. It is it's actually a vector pair matching analytical method in the scene, and providing the transformation in the space like X, Y, Z and their rotation for the next algorithms. The second one would be a machine learning algorithm, which is based on deep learning technology with the neural network and some kind of also analytical approaches to the problem. And this one is providing us solution for the case when we don't have a CAD file, or we have in the bin always something else. Like you can imagine you have a lot of things in usually in e-commerce, right? In one bin you can sort out the purchase order of a customer to have multiple things in one bin. And this this AI machine learning algorithm is best for also the food industry, because you cannot predict the shape of the food usually, right? So we have these two strategies, and they both work with Beam Picking Studio. So you just need to decide what I'm going to do. I'm going to be in a factory and handling the same thing all over again, or I'm going to be at the shop or at the stock or something, and I'm going to have a different object every single time. When I have the position from either of algorithms, I need to do path planning, because when we reach into the bin, we definitely don't want to, break something. Mainly the gripper robot, also we don't want to damage the part. And if you have some rotation of the object, you cannot access it from the same position every single time. If I will take a look at it as a simple math problem to match two different rotations, I would definitely damage something in a short time frame. So what we need to do is to do some kind of path planning and collision avoidance to put everything into one environment and tell the robot, don't go over here, don't go over there, because you would smash something. And you can have various potential obstacles like the bin, like other parts inside the bin. The gripper part is going to scratch something in the bin. You will have a scanner on top of the system, or you can have a scanner attached on the robot. Constructions, robot itself, everything you can imagine would be a possible danger for the robot, a possible collision object. And for that sake, for that thing, we have a path planning in simple environment, which is something you see on this animation. Robot is reaching into the bin and avoid everything with its own kinematic chain, right? And this is more advanced path planning, where you can literally see the robot is avoiding this wall in a complex manner. This is for the deep bins, and you have a full path planning, and the robot is trying to avoid this obstacle every single time. And usually when I take a look at this animation, I literally think about how it resembles natural motion. So it is not that common stuttering of the robots inside some path. This trajectory is computed with algorithm which try to bend the path like the human would do. Yeah, I have an obstacle in my course and I need to bend my trajectory, so I would do a curvature or something like this. And this actually resembles the human motion, in my opinion, at least human motion very well. So it's becoming a little bit frightening for me. All right. In this moment, I would like to go to the beam picking studio. So I'm going to take a look at the Q&As. All right. We can have a short break for the Q&As because we have just two, and then we can take a look at the beam picking studio actually. So does beam picking studio work with ROS? We support ROS, robot operating systems. You can take a look at our repository in GitHub. So we have a ROS package for the Foxy camera. Beam picking studio is a bundle of everything. So you receive the scanner, you receive the software. You don't need to work with ROS. Yeah, I'm not really sure how would you want to implement it. Maybe leave next questions for the next round of Q&As, and I'll try to answer it. And for the ZF Slovakia, how do the empty KLT bins get removed once empty for the robot to start picking from the full KLT bin underneath? This was a simple solution for the customer because they did not remove the operator. They just put one operator on multiple machines. So the operator has 1/8 of the time needed to spend on the machine. When the first layer was empty, there was a buffer of 18 parts already in the small conveyor. And these parts in the small conveyor were enough for the rest of the machine to continue for the whole minute, operation for the whole minute. And the operator was able to remove the empty bins once they were empty in this 1 minute because they are so light. So that was a simple solution to the problem. The operator just came in, hit pause, the rest of the machine continued from the conveyor belt, from the buffer, and the beam picking continued afterwards on the reset button. So right now I'm going to stop sharing this presentation, and I'm going to switch into the beam picking studio. And this is actually like a clean installation. What I did is I just logged into the beam picking studio. I can log in again, why not? So I'm going to use the credentials. and I'm going to log in. After login, you see a list of the solutions. This is your main screen. You can access it in here. The whole interface, as you can see, is a web interface. It is a great thing to use because I like it, because when I work with multiple projects, multiple solutions, I just open up new tabs over here. You can see it, and these tabs, I can have them open like 30 at once. Also, I can take a look at it. If I would, for some reason, want to, I can take my cell phone and access the Mimicking Studio and take a look at it, tablet or the laptop or everything else. So this gives us plenty of room for improvement and for the user interface into the future, right? With the clean installation, you receive a couple of example solutions with multiple robotic brands, with multiple objects. So you can see, you can take a peek into I don't know, for example, this UR10 with wide path planning range. Okay, I need to open it like this. Right, I need to duplicate it, the solution, because it is protected by a manufacturer, and I can access it and take a look inside the solution. And it is loading, or on the top you can see the bar is loading the solution. It takes a couple of seconds to load everything from database, but then you can go through the user interface. On the left there are multiple tabs, and I will go through them. So you can see there is a robot, there is a gripper, selected, some kind of object. We are going to pick some gripping points, predefined, then grasping, everything, right? I'm not going to skip. I'm going to explain everything. So you have these example solutions. You can import or create new one, and I'm going to create new one in this webinar. So you can see it is pretty easy, and it will be Mimicking Studio webinar. Today is 27th of May, and yeah, I'd like to put some meaningful description. And hit the save. So this is my Mimicking Studio webinar 27th of May, a project with some meaningful description. Today I'm going to use UR5 E series. So it's UR5E E series robot. This blue guy, I'm going to check the sticker. Yep, because I made a mistake recently that I didn't check the sticker for the right model. So make sure you have the right model selected. Otherwise, it would behave like it is not accurate or something. This is it. Inside the Mimicking Studio, there's nothing else you need to do for the robotic side. Inside the robot, what you need to do is, in here, in case of universal robots, is USB port. You put USB stick into the USB port, open up documentation, and follow these steps. How to install the files we provide to you. If it's universal robot, these are URP scripts. If you have a different manufacturer, for example, ABB, you have rapid files, right? And you have a step-by-step manual how to set up your beam picking. The very same is for all these brands: Denso, Doosan, Fanuc, Kawasaki, and so on, so on. So what do you need to do? What I did yesterday is I plugged in my USB, I followed these steps. Not many, you just need to upload some files, set up the IP address, maybe implement the gripper functionality, like open gripper, in the functions, and yeah, that's it. Not much of the work. I usually get it done in 1 hour. You can have it in 1 or 2 hours too. So this is for the robot in the robot side of the problem. Next would be the gripper. And you can see I already have multiple grippers in this setup, because there are a lot of other solutions, and you can share the gripper amongst the solutions, because you can have one machine and 20 different solutions, so you use 20 different grippers. You have a tool changer and so on. And today I'm going to add a new gripper. It will be called vacuum suction cup. And I'm going to browse for cat file, and it is on my desktop. This is the one. Click on the save, and the gripper is being exported into the database. What you need to check is if your gripper is okay. If your gripper is correctly modeled, like the X, Y, Z coordinates of the origin should be, not should be, needs to be on the flange of the gripper, right? Because this is the very spot we are going to place it on the robot. So that's just one mandatory thing you need to think of when you're uploading the gripper file. And but anyways, you will see it in visualization later if you do it wrong. So keep in mind to put origin of the cat file into the bottom of the gripper when there is a flange. And the next step would be, I'm going to save it to be sure. And the next step would be configuration of the tool point. And the tool point needs to be, in the place of the tool. Usually I like to put it a little bit further away, because that way I'm not going to touch an object, instead of going a little bit too short with the distance, and then I will smash the thing. So what I usually do is putting this one a little bit away from the actual tool position, like a couple of millimeters, so I can see it. And then when I start my beam picking, what can happen is I either pick it, or I will be a little bit too far away from the part. So nothing happens. When I do it in opposite way, I can damage things. So this is the reason why I put a little bit more, and I could expect that I'm not going to pick it the first time, so it's not biggie. I just need to take a look and see, okay, I need to decrease this number for 3 millimeters, and it is done. And then we have a rotation invariance, which is a property of the tool. And basically with this, I'm telling the robot, not the robot, but the beam picking studio, that my gripper can rotate and the functionality remains the same. So it can consider multiple orientations of the gripper during the path planning. And this gripper is actually too symmetric for you to see it, but this preview tool, point invariance slider, will show us all the rotations of the tool. Right now I'm going to leave it as it is, because it is a great number. I think it will be plenty for my solution. You can limit the rotation for only half of rotation if you wish, or 3/4. This depending on what's your gripper. You can disable some tool points. And don't forget to click on the save button. This way I have gripper created. I just need to select it. So it is vacuum suction cup. I just generated, right? This one. There are similar grippers already, but this is the one I just created. Then for the picked object, we have this plastic T fitting. The very same applies in here. I go with T fitting and maybe plastic. and you might put some description. It is not mandatory, and browse for the CAD file. This is actually mandatory, and my plastic fitting is right here. So I'm going to open it, click on the save, and while it's loading, actually a volumetric model of the part is generated, and the volumetric model is something like, maybe some of you know the Minecraft, the game. This is something you can consider. A volumetric model being is like something in space being simplified for the cubes. It is for trajectory correction for the collision avoidance, and the simplifying is because of the computing power we have. We don't have unlimited computing power, so we need to be, not very hungry on resources. And that's it. I just need to save it. So my model is uploaded, and I'm going to generate a couple of gripping points for the model. So this is me telling BIM Picking Studio how to access the part with the gripper. So in this case, I hope you can hear me. You have this T-fitting. I'm going to pick it from this side, and also this side maybe, if it is standing like this. So I could cover multiple rotations. So select plastic T-fitting. In general, you can have up to 4 different objects per one solution, and up to basically infinity solutions. This is depending only on your disk space. One solution usually takes anywhere from 50 up to 300 megabytes. So you can have up to, let's say, I guess 100 solutions. You would never cover this large amount of, not 100, 1000 solutions. But the machine would never, cover so many different workpieces. Anyway, for the gripping points, I'm going to select appropriate one for every single workpiece. Picked object, I need to create a gripping point. And it is simple because I'm going to use the very same visualizer as before. And what I'm going to do is just rotate it 90 degree. Okay, I see this is 90. And take a look from the side and maybe move it a little bit to the top. Like this, 29. I like to round up the numbers because it is easier to remember than, maybe it's a little bit too much. 27. 26 looks great to me. And also I need to do a little bit further away. Yeah, like this. 20 millimeters go in here as well. Okay, and this is me picking the part from this left side. And if I take a look, okay, but can I pick it from the top or from the right side? The first thing that come into my mind is I can create a new gripping point from the left, from the top, from top right, from the right, and I will have 5 different gripping points. But what I can do is also enable rotation invariance for the workpiece, set up the axis of symmetry, which is X. Yeah, it is X. In my case, move it to the center of this quasi-symmetry. Yeah, and you see, okay, a lot of gripping points were generated in a short time. So I have gripping points all around the part, and now you see this lower and upper limit, and I need to put 180. So I will not go all around the part. Let's demonstrate. I have 360, and I am going to rotate it. And yes, this would never work because there is an opening from the bottom, so I cannot choose this one. Also, I go to 180, and this is more reasonable setup, right? You can see from the left through the top to the right. And yeah, it looks good. This is something I would like to have in my setup, but also I see a problem in here. As you can see, there is a small, I don't know, opening or something in here, and this could make a leakage of the gases into the gripper. So what I do is usually I don't start at 0 degree, but I start elevated for, let's say, 10, and end up with 170 as well. So I'm not going to touch this opening, maybe a little more. Yeah, and this would be a better scenario for me. So I'm going to cover the whole continuous surface on top. Click to save, and I'm all done with this part. Repeat this process with all the workpieces you have in your beam picking, right? Take a look at the gripping points again. You will have many, depending on how many workpieces you have, and how much differently you pick them. So you will see a list of all them in here. I'm going to take a peek into the chat, just to be sure that there is no problem. Okay, I see no problem, and I'm going to continue. Maybe I just want to ask you, is everything clear? Like, can you hear me properly? Should I slow down, or maybe otherwise, should I increase my tempo? Or is it okay just the way it is? Yeah, so far so good. Thank you very much, Mr. or Mrs. I will continue now. For the grasping method, this is something like a blueprint for the trajectory. We in Beam Picking Studio, we get all these informations I put in there so far, like the tool position, then where the part is from the scanner, where the part is, and we are going to generate a grasp position, which is basically two systems overlap. Yeah, so we have this grasping position, and we would start over here and over there, my beam picking part of the cycle, then it will be loading to the machine, but this is something we're not going to compute because it is always the same path from the end position of beam picking to the machine and back. So I'm not going to cover this. And we are going to start somewhere. This is actually something we teach inside the robotic program, right? Going through grasp and going to end somewhere. And in the middle, we have a couple of more waypoints. We generate waypoints in the space to actually help path planning. And why we need to do it is because the path planning can be a slow process. It will explore millions and millions of combinations of the joints because it is basically a 6-dimensional space. I mean, the 6 joints of the robot to cover. And it is a lot of math, a lot of number crunching for the computer. And if we can think about the beam picking for a couple of minutes or hours and then set up the grasping method correctly, we can save 10, 20 or 30% of the cycle time, which can lead to increase of revenue and everything. And usually it is Start is very easy. We just set it inside the teach pendant and we can maybe call some procedure. These procedures are in robotic program and are empty by default, and you put digital inputs, digital outputs, analog outputs in there, so you can control the beam picking during the beam picking. It is a very easy, convenient way of you doing it. Then when maybe usually I call detach at the start, so I don't have something in my gripper when I'm starting. Then we go to approach, and some scenarios, not really this one, but when I'm taking a look at this part, I'm not really sure if you can see it. There's a little bit more light in here, but some scenarios require, for example, you are going to pick it from the side like this one, or through the middle with eccentric gripper, which is opening from the center. So you need to go into the middle, and the part, if the part is rotated, you need to not go straightly to the part, because if you want to go to the part, you would smash it, right? So you need to take a place before the part opening. For example, if the part is like this, you can see it, I need to go to this position before I can enter the part within my gripper, you know. And this is done via the approach waypoint usually, and the approach is looking for the grasp position. Then via the found gripping point we generate an offset. Remember, the Z is facing from the gripper, so if I want to go before the part, I mean behind it, I need to go in negative Z direction, and in my case it is, I don't know, 20 is enough. Minus 22 centimeters is enough. And also maybe in my case 10 would be enough, because I have a suction gripper and I'm going for the surface only. What I can do is to call a procedure name attach, because when I have vacuum gripper, I have a part which is loose in the bin. I want to enable the vacuum, then touch the part. Otherwise, since my vacuum is made from the rubber would, flink away my part, and I would result with no pick. So I'm going to enable vacuum right here and then proceed to the grasp position, which is with precise position tolerance, so the robot will stop in there, and maybe I can call attach procedure just to be safe again. Afterwards, I have a part attached to a gripper. I would like to retrieve it. We call it the approach waypoint. It is not actually a word, but we usually call it. So it's after the approach, it's the approach. And right now I have two simple options: to use robot or fixed plane. Usually for this waypoint, it is the best scenario to use these two, robot or fixed plane. The robot is the simple, in the robotic world, in the base of the robot, there are X, Y, and Z coordinates, or we can use these coordinates to generate an offset. And why we use the robot, not the found gripping point? You can use the found gripping point. It's a no problem. If you use 10 or minus 10 millimeters, you would go to the part, pick it, and the very same way you would go out of the bin. But usually, if it is accessible for the gripper, it doesn't mean that the way is accessible when you are dragging the part with you. And what I mean by that is when we take a gravity into account, and the part's usually falling from the top to the bottom of the bin, right? And when we are taking the gravity into account, usually the best, the most, how to say it, free way, the most open space is directly upwards. And with the robot standing on the XY plane like this, it is a Z direction of, let's say, I would like to fetch it. Okay, the worst case scenario is 120 millimeters, because the bin is 120 millimeters deep. So we will end up literally right above the bin. And the path planning from the middle of nowhere to the middle of nowhere is, like this, very easy task. And just to be safe, I would like to put 150. But what happens if my part is on the top of the bin is full? I will end up with going 150 to the top of the bin. This is not really an issue with the shallow bins like I have in here, but what if I have 1 meter deep bin? Then I would end up going from the bottom to the right to the top of the bin. But if I'm going from the full bin, I will end up 1 meter in the space. And this is not actually something I would like to recommend or I would like to do, because the path planning would be painful and everything. And in this case, I usually set up a fixed plane. And what is fixed plane? Okay, remember, if you forget about anything, you go to documentation and, for example, picking path stages. And all right, with picking path stages, I'm going to search for fixed plane. And you see this nice animation explaining what is the fixed plane. The fixed plane is just a plane in the space. It's something we made up. And we will retrieve the parts to the exactly same height every single time. It doesn't matter where the part was. So in my case, 0 would be literally at the height of the base of the robot. This robot has its XYZ coordinate in here, like it is visible in this picture. So if I want to go 5 centimeters above the bin, I will put 550 millimeters in here. Click the save, and this is it. This is my grasping method. I hope it will work fine. From the first run, we will see. I was talking about the vision systems during the presentation, during the slides, and right now we can see we have a bin picking studio. If I open up the solution tab, all of these are made with the CAD-based localization engine, and this is the analytic one, and we are going to set it up really quickly for us to see. The name for this vision system would be, I don't know, it will be T-Fit vision system, something creative, right? And what the vision system actually is, we have a lot of resources, like we have these work PCs, we have the scanner IDs, we can have multiple scanner positions. So one vision system is one group of everything. First of all, it is the scanner ID. I'm going to use one of the available scanners. This is one I have attached to my gripper cell, the one over here, right? 17090004. And the scanner model is scanner M, medium sized, and it is placed on the robotics cell, right? Just vision system with static scanner on top of the cell, some kind of description. And the big object is just one object we have in here in this project, and it is plastic T-fitting. What I need to do is to turn off deployment before I start the vision system. If I don't do it and go literally to the process, the bin picking will tell me I cannot create localization profile while deployment is running. So what I need to do is open up a new tab like this one, stop bin picking, wait a couple of seconds until it shuts down, and I can create a new localization profile. If there is any problem with your bin picking project, the bin picking will always tell you you're doing something wrong. How to set up a localization profile? Maybe that's your next question. I like to do it like I rush into it, start localization, and see what it do. Yeah, usually it will generate a good results straight out of the box. Okay, I see some lagging because of the presentation. I'm not really sure what is happening, but I will try to do my best to show you how to fine-tune this vision system as quickly as possible. But I'm afraid there will be no fine-tuning because it actually finds a lot of parts. Yeah, I think every single part is found in the bin actually. Is it true? Yeah, it's really strange. But okay, I see some problems in here. Like this part is rotated. It's clearly rotated, so we have a false positive. And the first thing which came into my mind is what overlap it have. And I'm going to find it in this section on the right. What's the overlap of this part? No, it's not this one. Yeah, it's this one. It's 24 millimeters. Oh, not millimeters, 24%. And this is basically BIM Picking Studio telling me that I see only 1/4 of the visible area, not the whole area, the visible area. And I can increase this number to limit out false positives very easily by, I don't know, when I take a look at these numbers, everything reasonable is over 50%. So I'm going to put 15 there. I started new localization, and now I can see only parts where I see at least 50% of the visible area. And what I see is almost everything, just couple of parts missing, and these parts are usually the ones we cannot see in full. And it's usually not a problem because they are covered with something or they're in position like this, so I cannot pick them anyways. And you can see, all right, there is a lot of other settings, specifically in advanced settings page, and I can cover them, but not in this short webinar. I will cover them in the BIM Picking Become a Pro session. This is a whole day session where I explain every single part of the BIM Picking Studio. So make sure you join these tutorials, these trainings as well, if you want to know about the BIM Picking Studio more. Right now I'm satisfied localization. Maybe I'll put a bounding box really quickly. A bounding box is just a region of interest for me to tell BIM Picking Studio, okay, not pick from the right bin because, you know, I have a right bin as unloading bin. So I'm going to move and rotate it with the help of these arrows, like this. Okay, so this will be my region of interest. If I want to have it a little bit more, you know, if I want to be a little bit more specific, I can limit it to exactly correct position. Yeah, I feel you being bored by this, so I'm going to do it as quickly as possible. This is something you would do usually with the region of interest, with the bounding box. Put a small bounding box around your region of interest. And okay, I want to start locate before I save the configuration. And you can see effect immediately. You will not see any parts in the right bin. You can see some segmentation being done. That means the point cloud have a green color, but the actual parts are not in there. And this is only the segmentation, the algorithm, which is like a pre-processing. So I'm going to save it and continue with my bin picking setup. Quit localization, and to close this interface, And now you can see almost complete vision system. There is two more options. Gripper collision sensitivity. It is telling me how much of my gripper can be in collision with the point cloud. This setting is literally tied to the other setting. I'm going to find it. And it is resolution of the point cloud volumetric model, right? By default, it is 1 centimeter cubic. So 1 cube is the smallest point in space we have, a smallest, like, imagine a Minecraft of your of your point cloud. If the scene is small, the robot is small, everything is small, I'd like to recommend to reduce it to, for example, 2 millimeters, and tell that everything below, I don't know, 2 points in these 2 millimeters cubic is just noise. So we filter out noise, or maybe 1, and everything will be considered. Right now, maybe I'm going to leave it by default value, but this strongly depends on your setup. And you are telling, okay, less than 5% of collision is basically just noise, so this is good threshold for me. And the last one is the fast scan. And the fast scan is an algorithm which will take a two-dimensional texture from the last scanning. Then the acquisition of next point cloud is hold. You get only two-dimensional texture again. When the part is missing, you will see it in the texture. So okay, these points from point cloud are no longer valid. So 5% of point cloud should be erased. But the remaining portion, the 95% of the point cloud, remained untouched. So you don't need to do anything with it. And you can save some time. I mean, the scanning can take from 500 milliseconds up to 5 seconds usually. And if you can save 4 seconds from cycle time, it's usually a great deal. So we are going to tell, do scan every 5 cycles, or if you cannot find more than 3 parts in the scene. And also make a new scan and new localization when there are at least not at least one. This is being when there is nothing to pick, or at least 2, so you have something in the buffer. This is a good setup for me. I'll usually only increase the full scan frequency, and that's it. The vision system is set up properly, and we will see very quickly in a short time how it behaves. The calibration was done by me in a while ago, so I don't need to recalibrate the scanner. The calibration is basically position of the scanner being saved into the beam picking studio, so we know how to translate the point cloud. If we will have some time at the end of the Q&As, I suggest we will do the calibration all over again. It will take like 10 minutes, 15 minutes. So it is a very easy process. The process is usually putting a small spherical object, a ball. Ping pong ball is really a great tool for this, because there's most abundant thing in the sports shop or every single shop. They are manufactured with great precision, literally 1 or 2 orders of magnitude better precision than the accuracy of the robot. Sorry for that. And they're small enough to fit into the gripper. So the calibration was done. Was done, but on a different solution. So my options are either recalibrate or going back to the solutions page, open up. Okay, I don't have it in here. Why not do a calibration? It will take only a couple of minutes. So during the calibration, I'm going to explain, select radius of your ball, like this one, and attach the ball to the gripper, like this one. Remove the bins from the scene. Why is that? Because we are going to calibrate inside the volume of the bins only. In that way, we can compensate for inaccuracy of the robot. And remember the slide from the presentation, we need that extra accuracy. And navigate the robot to the multiple positions. We need to have 9 positions and click add calibration point. And the beam picking is telling us, okay, I have the calibration point, or something is happening with the texture. The calibration point was added successfully. Navigate to 7 more positions. Okay, I cannot see the whole ball. I think because there is a hose doing the shade for the ball. So if you have an error, then the beam picking studio will tell you. And what I usually do is I'll cover all 8 corners of the bin and also place one into the middle. And what you can see is the output of the calibration process, and there is some estimation on the position of the scanner, and each single one has some inaccuracy in it because the system is not ideal. The robot has some inaccuracy problems. So you see there is estimated accuracy of 1.27 millimeters. In math theory, this is the sigma 1 number, and provided you did a great job on the calibration, you should expect 67% of the peaks within the 1 millimeter radius. If you want to know approximately 99.7% of the peaks, this will be within 3 times sigma, so it will be 4 millimeters. It could be better, but it could be worse also. Pay attention that I just mounted the ball onto the gripper, so it is a little bit loose. If you want to have better calibration, mount it perfectly somewhere on the gripper. Doesn't matter where, but it needs to be, not wiggling, wobbling in the space. It needs to be, it needs to be firmly attached to the gripper. And also what I can do is to do a verification where, provided I have robot started, because I need to start it to do my calibration, I can navigate robot underneath the scanner. No, a little bit too strong. And trigger a scan, a plain scan. It is. Maybe I'll change the color of the point cloud. And you can immediately see that the point cloud is matching reality. You can even read out the logo of the robot. It fits almost perfectly. Yeah, there is a 1 millimeter of deviation, 1 or 2 millimeters. That is no biggie because the gripper is usually not that precise. When you are teaching positions in the factory, when you have welder and everything, this is a different story because you are working with repeatability. In beam picking, we are working with repeatability and accuracy. So that's why it is important. All right, but now I'm more than satisfied with the results. I'm going to finish and save them, and I'm going to continue with the beam picking setup. And the next step would be environment builder. And this is the last step before we can actually run a beam picking solution, because we put everything around the robot into the environment. Again, I'm going to put them back into the correct position. And what I like to do is I will begin with the help of the vision system. And I'm going to connect to the T-feed vision system with the already calibrated scanner. And also I'm going to navigate a robot to the start position. Or at least to the home position. It doesn't really matter. And then I am going to, first of all, trigger a scan. So I will see where are my bins. I can already see a scanner in here. The bins are underneath the scanner. And also when I switch to the robot page and in Radiance, I can read out my starting and end position, which is literally this. This is my starting position and the point cloud, and these will help me with building the environment and checking if I have a wrong or correct CAD files. So I'll begin with the scene tab, add object, and go for upload STL. And if you have an STL file of your environment, just put it in here. And this will be my robotic cell. Type is environment because this is an actual environment. And I can see the rotation is incorrect. Position looks good, but rotation is incorrect. So go to the robotic cell, navigate open up the robotic cell, select object rotate, rotate along that. Yeah, I see it is 90 and whatnot, right? 90 looks good. Also, I see a small deviation in the X rotation. You see the red is X, And this will be, I think, 1 degree, -1. -1, and it looks good. Okay, it fits great, and I can move on. This is the position of my scanner. This is my robotic cell. Save the scene, and I'm going to create a child object for the robotic cell, and it will be bin left and bin right. So I'm going to upload those bins as well. The bin object is marked with blue color, already in the place, very good. And the next one would be similar, bin 2. Okay, one of them should be on the left, so I will select the bin left and move it to the left. Yeah, very simple, right? Check the position if it is matching with the point cloud. The right one is a little bit too much on the right. No, it's too much on the left. I'll move it a little bit to the right. And this is the correct position. Also, behind my back, there is a wall. So I need to put some kind of, virtual environment object to the scene, so the robot will never approach the wall. And I'm going to create a new one from the box, because why not? And just resize it in this direction, and also is just over here. So the wall will be protected by this virtual collision object. And rename it wall behind. Save the scene, and well, it looks good to me. It looks great. I think there is nothing else I should do. Let's start the beam picking. So I saved the environment. I will deploy this solution right now. I have all these green checkboxes. So everything is complete. I don't need to change anything if I want to start it. What I'm going to do is I'm going to reduce the speed. 25% would be plenty for me to observe what is happening. So I'm going to scroll to zoom into the visualizer in here. All right. And also I'm going to start my robotic program, and I hope you guys can see it. So I received my point cloud. I will change the color to the black, so you see the colors of the parts. And you can see also the trajectory of the part which is being removed. And me looking into the bin, I can see that the part was like 5 millimeters away from the gripper, which is what I was totally expecting, because I put the gripping point a little bit too far away. So I'm going to stop it. You see a lot of parts being green. That is good, because the green color is something which is already in the memory with pre-computed trajectory and everything. I'm going to open up webinar, open up the gripper, actions, edit. In the tool point section, I need to change the number from, I don't know, I'll remove 5 millimeters, 87, 86. Click to the save. And in here, I'll click restart beam picking. So the new values are being loaded, and the program, I'll just restart the program from the beginning. Beam picking is ready, so start the program. All right, it was still too far away, so I'll need to reduce it for. Okay, I was edit. Okay, I see that this is my fault. I need to stop beam picking, and right now I can edit this one. So remove those 7 millimeters. Click on the save again. All right, and 2 point has been updated, and now I can start beam picking again. Okay, that was my fault. Sorry for that. And the beam picking is ready. Start. All right, I'm not really sure where it becomes boring, but I see 3 successful picks, and I'm really satisfied with the results. So I'm going to stop the robot, and I'm ready for your questions. Can you see the beam picking is working? And all right, I'm not really sure what else to say. Going back to the beam picking studio, there are a lot of other settings which I didn't really touch because these are predefined and usually working out of the box. But if you need to fine tune some knobs, fine tune some buttons, these are in here, and you can do them by yourself if you know what they do, and you can learn what they do on the beam picking training. That's it. Thank you for joining. Have a great day.